Welcome back to part 2 of this week's Apex lesson. We're going to start back where we left off, which is on page 10 of the 22 kind of slides that are for this study lesson. We're back and looking at a problem from scratch. Okay, we want to know the enthalpy of this reaction up here. We've got C2H4 plus hydrogen gas yields C2H6. So we know that we can take these three intermediate reactions, meaning three parts of reactions, and we know the enthalpies of all of those. Well, how can we combine that so that it equals the total up top? Okay? Now, the whole idea is that whatever we do to equation, whether we reverse it, we have to, add coefficients to it, the same thing has to be done to the number on the right. So whatever you do over here, whether you flip it, change it, you have to do it on this side too. Okay, let's get started. So, the tricky part is to know when to reverse, when to multiply or divide the reaction so that it comes out correctly. Okay? Now, at the original equation, the ethane, C2H6, is a product, and it only appears in reaction 3, so this reaction's gotta be reversed. Okay? When we reverse a reaction, okay, to make it in there, you have to change the enthalpy from the sign, whether it was positive to negative or negative to positive. Okay, and I'll show you a little bit more in the PowerPoint coming up. So in the end, we then set it up. They've color kind of coded it so that we can know what cancels out. So like this half of the oxygen plus these three O2s can cancel out with the 7/2 O2, like that cancels out completely, the pink ones. This one water plus that water equals 3. Well, there's 3 over here, so those cancel out. That's why they don't show up in the end. We've got 2 carbon dioxides here, 2 carbon dioxides here. When we, they cancel out, so they don't show up. So all you're left with is this H2 over here, this C2H4, and all you're left with is this one. There's nothing to cancel it out. To then find the total over here, you then add up every single one of these numbers, and in the end you get negative 136. When you added negative 286 plus negative 1410 plus a positive 1560, you get this number. And that's it. Okay. So before we kind of get into this, I'm going to show you a little bit on the lesson of this. So the whole idea, what did I mean by reversing? What did I mean by multiplying? Okay. Sometimes we need to change sides with the products and reactants. Maybe water's on the product side, on the right side, but it needs to be on the left, on the reactant side. So all I do is I change the sign from, negative to positive. So for example, if I wanted to reverse this, I wanted to get PCl3 on this side, and I wanted, phosphorus on the right. So all I do is I just switch sides so that 2 PCl3 is on the left side of the arrow, these two on the right. And then what I do over here, I just make sure the signs are reversed. That's it. Okay, so sometimes that has to happen is where you have to flip them so that I can make that all equal. Now, sometimes though, I need to also multiply or divide what's going on. Okay, what if the coefficient isn't the same? I've got 2 waters on one side, but I needed 2 on the other, but I don't have 2. I can multiply it. Okay, so what does that mean? So maybe I needed 2 calciums instead of just 1. Okay, well, I can multiply this whole thing by 2, okay, and so that I get 2 calciums, 4 carbons, and 2 of these, and then what I do is I just multiply that by 2 as well. So whatever you do on the equation side, you're going to also do with the enthalpy as well. So that's all it is, just remembering whatever I do over here, I'm going to go over there, okay? And you can combine them you can reverse and multiply by 3. Say I wanted to flip it over, reverse this, switch sides, times it by 3. You can do a whole bunch of combinations. Reverse the sign, times it by 3. Like, it all can be combined. Okay, there's nothing like that. So, going back to this. So let's look at the questions here. Okay, so on the question here, which of these 3 chemical reactions must be reversed before applying Hess's law? So I'm looking in here, okay, I've got this on the left side, this on the left, that one on the right. Is there something that's out of place? And as I go through them, I kind of notice, oh, wait, C2H6 on the left side here, but I want it on the right. It's kind of the only one that doesn't, like H2's right's on the left, this one's on the left. This one shouldn't be on the left, it should be on the right. So I'm thinking reaction 3. Okay. So just kind of hunt and look. You look to see what's out of place. Okay, so do all the water molecules cancel in all three equations? So let's see. I've got one water here, one water there. What's on the right side? Nothing else down here. On the left side, none. Oh, there's three on that. So there's two on the right, three on the left. No, they don't cancel out. There's not the same number on both sides of the arrow. So now that there's unequal, we've got to see which one should we multiply 2 by to make the water molecules cancel. I think it's this one. Partly because I think if I put 2 here, would that be too many? I don't need 2 there, and that's too many. So I'm going to go for reaction 1. Okay. Now, you've decided that hydrogen and oxygen should be multiplied by 2. Okay, we did that. Example 3, do all of the intermediate molecules cancel out? Let's see, are they all good? I got 2. Yeah, I think they're all canceling out. They're ready to go. Yep. Okay, now what I do, I forgot to pull up the calculator. So when we find out the total enthalpy for the whole thing, well, I've got to add up all of these numbers. So I'm going to take 572, negative 572, plus negative 1,260, plus 1,560. Okay, so equals negative 272. Yeah, that's one of my answers. That's correct. Okay, and then congratulations, it's right. Great work. Okay, so we're ready to move on a little bit. Now we're going to throw in some ideas of moles a little bit. Okay, so and kind of also this page is kind of talking about why do we need this? Why is it useful to know? And a lot of it is because we need to know what energy is required to do a lot of things. A lot of with the chefs, computer engineers, just named a few, they kind of look into this energy, this enthalpy that's produced for every mole. Okay, so let's get into this last idea. Now these moles, we got to remember, we kind of need the periodic table a little bit for this, because they're trying to, step 1, we've got to convert the mass of propane, which is C3H8 of to moles. Now, we know the molar mass of propane is 44.09. What? Where in the world did I get this? Remember what I told you, whenever they say molar mass, guess what you need to look at? You need to look at the periodic table. Okay, the how many carbons they have, well, 12 times like 3, how many of the hydrogens they had, times, and you add them up. Okay, that's where they got molar mass. Now, they luckily gave it to you. Okay, when we set it up, we have 1 kilogram, I need to go to grams, so 1,000 over 1, okay, times 1 over 44, because remember, grams should cancel out, that's why we put it on the bottom. Okay, all you do is multiply across the top, divided by the bottom, and you get 22.68 moles of C3H8, okay. So let's try this one. So we went to moles, okay, of propane. So that's how much, we know that 2,220 kilojoules of heat is produced. So now we want to know the amount of energy released burning this much amount of propane. So we have this amount of propane, 22.68. We know how much kilojoules per 1 mole. Well, we have this many moles. So we're just going to multiply across the top, and you get 50,349.6 kilojoules of heat if you have that much propane that you're burning. Okay, you're releasing that much energy. Okay, but the problem is, okay, we have propane, we're heating something. Well, how much, what do I need to know to calculate the amount of water that I can boil if I'm using this much heat? Well, we need to know how much energy it takes to just boil water. Okay, so when I use the amount of heat it takes, how much moles, so all I gotta do, okay, step 3, convert the heat produced to moles that can be heated. Okay, I know I have this much heat available. I just calculated it the last time, that was on the left side. Okay, I know that for every 1 mole of water, it takes 40.65. Okay, this is where I got it, 40.65 kilojoules. So I just multiply across this number times 1, divided by 40. That's how many moles of water I can boil with that much heat. Okay, that's how much water with that much heat of propane. Okay. So, in the end, we then just convert to volume. Okay, so we know that's how many moles of water. We then know that 18 grams of water, where did I find the grams? I found it on my periodic table. Oxygen had 16. There was 2 hydrogens. That's where the 18 came from, molar mass of water. Okay. 1 milliliter actually is equal to 1 gram, so it's an easy conversion. And then I need to go to liters because I'm in milliliters right now. So what I do is multiply across the top divided by what's across the bottom. And then the answer is, so let's plug it in. So the answer is 8.6 times 18.016. And then you can times it by 1 times it by 1. I'm not going to because it's just itself. Divided by 1 times 1 times, so divided by 1,000 equals, and this is rounded to the nearest whole number, equals 22. Okay. Now, how much ice can I melt by burning 20 grams of methane? So we can use this by just converting and using these modes. Now this one's a little bit nicer because they give you all the conversions. You just need to line it up. Now remember, we used to do this in class. How do you cancel out things? They need to be on the bottom, and that's really just what they want. They give you the 2 options. You need to know, is the grams on the bottom or is it on the top? Okay. Well, to cancel out grams, you need it on the bottom. Okay, so that's correct. Mole, mole needs to go on the bottom. Okay, correct. What needs to go to the bottom? Is it kilojoules on the top? That wouldn't make sense. Kilojoules go straight on the bottom. So I want you to kind of work through that yourself. It really just calculates all for yourself, but you can finish it with it. Now the last little bit is putting it all together. So the very first part of this one, part 1, it was talking about graphite to diamonds. You needed heat to do that, energy. And so they wanted us to kind of use Hess's law to figure out how much it takes to change your graphite, your lead, and your pencil into a diamond. Okay. So we know that graphite, going to CO2, and then diamonds plus what makes CO2, you know these enthalpies. Okay. So how do we need to get them together? Well, diamond's on this left side right now, and it doesn't need to be. We want it on the right side. So you need to reverse the equation 2 first. Okay. I went ahead. Sorry. So reverse the question 2. Correct the next one. Okay. Then what we do when we reverse it, what did we always say? When you do something onto the equation, you have to also change it over here. So when I reversed it, I now need to change the sign of enthalpy for equation number 2. So I think it's C, if I'm reading it correctly. Yeah. Okay. Now, do these equations add correctly? If I look, I should think yes. It looks like it's ready to go. Graphite is over here, diamond's over here, everything cancels out. Okay. Now when I do this, I'm going to add up this. So negative 394 plus 390, so 394 plus 396, somebody you can get in your head, is just 2. Now it's a positive 2 because that's a larger number. That should be right. Okay. So in general, and at the last very part, it only takes 2 kilojoules of energy to turn graphite into diamond. That's crazy. And then they said it's about as much energy as you get from eating a hamburger. But on the other hand, you learned that burning a kilogram of propane just produces more than 50,000 kilojoules. Now, considering how little energy is required to transfer one to the other, why doesn't graphite just readily turn into diamond? Like, why don't my pencil turn into diamonds? We need to think about the other factors that are involved. And we've talked about this, diamonds, they need heat and pressure and different things going on. So try to identify, in 35 words or fewer, not much, what else might some of these factors be that why, graphite doesn't just regulate into diamonds. Okay. I wish you luck. If you need more help, I will try to help you out and give you other things. But that's where kind of the lesson ends and where you think you should be.